as a function of the base emitter forward biasing, whereas like another, I was wondering how that works because the scaling on that is actually dependent on the base minority carrier concentration, like Ni squared over the acceptor doping, as opposed to, I thought it would be proportional. I would think that the emitter injection would actually be proportional to the emitter concentration of electrons on the emitter side.
Right, up to a certain point, though, right? I mean, if think about it this way, if the number of electrons are small, the minority carrier charge is small, then what happens is that you're not affecting things. But at some point, you can have so many electrons on the other side that they can repel things back. That's very important. I mean, it's a second order effect. Let's put it this way.
Okay. Because then I was wondering how the actual built-in voltage ever came into play. Because if it's strictly relying on the base emitter biasing, then...
Well, it is something, well, it comes into play with basically determining the height of the barrier, which determines the steady state condition for the reverse injection current. That's how it comes.
Oh, just for the reverse injection.
Yeah, but I will be happy to talk to you about it over the break. We'll look at the equation. That's what. Any other questions, general questions about class or the material? All right, in that case, let's continue our discussion. So, what we did last time, we analyzed the MOSFET and we understood how it operated. We saw that when you apply, for instance, for an N-type substrate, when you apply a positive voltage to the gate, you attract electrons to the surface, so that was accumulated. But when you apply negative voltage to the gate, you actually started creating a depletion region first, and then beyond that, you had an inversion layer. And we saw that how we actually could use this inversion layer to make a device, a voltage-controlled resistor, by creating two terminals on the two sides of the surface. So what we did, we created this MOSFET where you had the oxide or the insulator in general, and then you had the gate material, which was some sort of conductor. We call it metal, although most of the time it's not made out of metal. And then we saw that we could have this device, and in general, it's built on some sort of a substrate. So let's say it's an NMOS. So we have N+, and then we have P substrate. And therefore, there are 4 terminals involved here, right? You got the source, which we decided was a reference potential. So this is the source. The drain, which we said in general could be connected to a potential VDS, reference to the source. The gate voltage, which was VGS, again reference to the source. And VSD, between the source and the voltage. Right? So you can see it's a 4-terminal device. And then of course what we saw is that at lower voltage, in general, to determine what the threshold voltage is, you have to take into account the effect of this depletion region underneath. You have this depletion region. Part of it is formed by these junctions, but the rest of it has to be formed through the application of this gate voltage. Now, the other thing you notice is that in general, this voltage will also affect the width of the depletion region in addition to this voltage, right? Because when you apply larger voltages, reference to this voltage, which is the reference for all of these other voltages, so you can actually modulate the width of this depletion region by controlling this voltage. And that's what we call the body effect. And it was responsible for a change in the threshold voltage. We could account for it as a change in the threshold voltage. So we saw that the actual threshold voltage that we had, the real, was the VT naught, which was the threshold voltage without the body effect, plus, you can write it as in the following form: gamma square root of 2pf plus VSV minus square root of 2pf. And we knew gamma was square root of 2UND epsilon silicon over Cox. Okay? Alright. Now, so that's what the threshold voltage was. But so we saw that there is a second effect, a secondary effect, this body effect that can control the current, because if you keep these other voltages constant, let's say your VGS and VDS are constant, right? And I apply voltage here, the substrate, the bulk. What happens is that I can actually control the current, the drain current. Why? Because I'm changing my threshold voltage, and then my threshold voltage appears in the expression for the current, which is as if I'm changing my VGS. But the relationship is a a little bit weaker because it's a kind of a square root behavior as opposed to a linear dependence. So it's not as strong, but still it appears in the expression. So for instance, in the pinch-off region, we saw that we had an expression square law dependence on VGS minus VT. So if VT changes, then of course that current can change for a given VGS and VDS. So that was one thing. And then the next thing, we said if we apply a reasonably large voltage here, what happens is that the voltage across here would be larger, so the depletion region would be skewed towards the drain. Because this is, and on this side you have a larger voltage, so you have a larger depletion region, and on this side you have a smaller voltage. Now the other thing that happens is that also the channel in general, when we had a channel form, which we showed like this, would have a smaller concentration of carriers, in this case electrons, at the surface on this side and this side. Because if you look at it across one point here, some arbitrary point, it's really the voltage difference between this point and that point that determines what is the excess inversion charge that you have. And that voltage is really nothing but the VGS minus V of X. So let's call this X. And that minus VT is what determines how much inversion charge you have. So the charge density is really that times Cox at any given point. Now we use that to come up with a simple expression for a charge in a slice of this transistor, in an infinitesimal slice dx of this transistor. And we saw that the charge in that, total charge in coulombs, was Cox times W times dx, which is the area of the slice, times VGS minus times VGS minus V of X minus VT. Well, there's an assumption here. There was an assumption here. And what was that assumption? We made a simplifying assumption, the way I wrote that expression, and it means that VT is constant across, right? So the VT is the same here and there, but we know that's not true because we know the width of the depletion region is different here and there. So really the VT is a function of x2, but for our calculations we'll ignore that because it's not a very strong function, it's kind of a square root dependence. And if you make that assumption, then we have ignored the bulk charge theory and we've gone to basic theory on the MOSFET. And we use that expression, so we calculated the current. So we basically said the current was, by definition, is dq on the drain current, this current, is dq divided by d tau, which is the time it takes an average electron to get from this side to that side of the slice. And what was that time? We calculated that too. So quickly review this. Here, d tau was what? Is the velocity, the distance, dx, divided by the velocity, v drift. Which was what? dx divided by, now the v drift here is what? We know if you are not velocity saturated, if the electric field is not too large, it's mu n e x in the x direction, the electric field, that direction. Which is what? Which is the voltage drop, we can write it as the voltage drop across here, dV, across that tiny slice, divided by dx. Right? And therefore we had dx squared over mu dV. And then when we plugged it into this thing, what we got was that you got that divided by this one, so you got mu n Cox W VGS minus V of X minus VT dV dt. And then what we did, well, dV dx. And then of course we integrated it from one side to the other and it gave us the expression. So we integrated both sides, I'm not going to repeat the integration, gave me the current, drain current, which was mu n Cox W over L VGS minus VT VDS minus VDS squared over 2. So we had this linear region, the linear part, which was a voltage controlled linear resistor, and there was a correction term. And this was basically associated with the triode region. And then we saw if VDS became greater than VGS minus VT, so this is for VDS smaller than VGS minus VT. And then when it became greater than that, so the first order, our expression, the current, became what? Well, to calculate it, we have to VT, the voltage drop across that, right? Across this channel. And now if you go beyond that, what happens is that this point is shifted. So what happens is that you have a channel only up to a certain point, but at that edge, you always, the voltage of that edge, V of x, the x of that point, is VGS minus VT. And so, as you apply larger and larger voltage here, most of that electric voltage or electric field dropped across this small region, this depleted region, this region that doesn't have charge. And therefore you had a relatively large electric field pointing in this direction, which could absorb all the electrons in, and a large change here resulted in a relatively small change in the channel width, and therefore, to the first order, the current would remain at what it was when you reached this region, when your VDS became VGS minus VT, which was basically mu LC ox over 2 from this expression, W over 2 VGS minus VT squared. But we know there's still this effect, secondary effect, which is basically the modulation of this length, the channel length, the effective channel. So we saw the channel length was modulated because of this when you change VDS. So it was not large, but there was that term. So we captured that as a second correction term, which was 1 plus lambda VDS, to account for the variations in that direction. And lambda, we calculated by the lambda, we saw lambda was basically 1 over L effective, ID over L effective, dxt dVds. Good break. I did it upside down. Yeah, it's actually 1 over L effective. And okay? So you see, ideally, do you want a larger lambda or a smaller lambda? Do you want this dependence to be strong or weak? You want it to be a weak dependence because you want the current to be only primarily dependent on VGS, right? These correspond to those curves, right? The ID versus VDS curves. So this is the larger lambda, larger the lambda, the greater the slope here. You want the slope to be as small as possible because you want this only to be controlled by VGS primarily. And therefore, what it tells you is that the larger L, the smaller lambda. So you have this degree of freedom. You can make L greater and therefore make this channel length modulation effect weaker. Now, one side note, if you look at, so these were the two equations we had for the two regions, the triode and the pinch-off. Now, if you look at these two, the way I've written them, there's a discontinuity at VGS minus VT equal VDS. Why? Well, I derived this part of the equation from that. So if I just drop this term, it is continuous, right? If I drop this term. But now I've added this correction term that makes it discontinuous. So if you actually go and plot this, what will happen is that you will see something like this. At that point. Which is an artifact of this correction term. So there are several different ways to deal with that. One is to realize that it is there. I've added the correction term here. And just as long as I'm not in this region, live with it, and use that equation in my calculation. Whenever I'm in trial, and use this equation to pinch off, knowing that there's this kind of error. The other way is, but that would be a killer if you try to incorporate that into a simulator. Simulators, or computer simulators, are extremely sensitive to discontinuity. Not only in value, but also in the derivatives. So when you make it, if you have discontinuity like this, the simulator can go nuts. Right? So this is what can happen. So let's say you're trying to find a solution for ID, right? And then it goes and says, the way it works, they are iterative, right? They're going back and forth and trying to converge to something. So let's say your solution is somewhere around here, based on the rest of the circuit. So it goes, as you can see, it jumps back and forth, converges here, and then goes back and forth, back and forth, back and forth. It never converges to something. And then it gives you a convergence problem, or kind of stops working, or something, depending on how it's written. So in simulators, it's extremely important to have this continuity. So sometimes, if you want to use these kind of equations, this simplified equation, you may want to have a modification here too. So you just may want to add that term here in your simulator. And if you put it there, then it becomes continuous. You basically just multiply both of them by this expression. without this correction term, you have that. Okay? So you have to realize all of these are kind of correction first order terms of the Taylor series. So it shouldn't be that strange if you do it. But nowadays the simulators seldom use these kind of equations. You have these simulation models incorporated in your simulators, and for some of our calculations we will use those. It's called level 1 model. It's the most basic model. For our analysis, hand analysis, these are more than sufficient. Right? Because we already know even these equations are approximate. But for simulators, there are more sophisticated models like BC models and then other kinds of models that have been developed that capture a lot of second order and third order effects, which is what you really care about when you're using a simulator. In a sense that you want to give you as accurate a result, as close to reality as possible. But for your hand calculations, you never want to use all those things unless they are really first order effects in a certain case, because it becomes completely intractable. You will see even with these simplified models, we have to many times we'll linearize them, and even with linearized model, we will have a lot of work to do in hand calculation. And then you may come back to me and say, well, what is the point of hand calculation anyway if it's not accurate? Why don't we just dump everything into the simulator and see what the answer is? So, what is the rebuttal?
Computers are only as good as the information you give it. You have to make sure you're doing
That's true, but let's say, in a way, that's kind of one way to answer it, yeah. But if I have all the information about a circuit I want to analyze, right? I just dump it into the simulator and get the result I want, right? So why not? Why bother?
It's more fun this way.
Okay, well that's another kind of logic, but it's interesting.
This model.
This is a fun activity for me, but there are other fun things I can be doing, so it's not necessarily just I just want to spend all my time doing this.
I think this model will give you more intuition about how the circuit behaves than dumping it into.
At least you have to, yeah, exactly. So to that part of the answer, so both of these, but and the fun part, of course. So all of them are correct answer, but yeah, you have to gain some. First of all, you have to gain some intuition, and you have to know what's going on. In other words, you have to. Let me give you this hypothetical scenario. So simulators are very good if you know what your end result is already, right? If you know how your final design, let's say you are designing an amplifier with 30 transistors. If I give you the amplifier with all the dimensions of the W's and L's of every transistor and all the values of the components and everything, you could dump it in the simulator and see what the result is. But this is not just an analysis class. It's a design class. So now let me ask you this question. What if I ask you to make an amplifier with the specifications of that amplifier without giving you the specs, without giving you the schematics? That's the design part, right?
Unless your ADS design kits.
Yeah, still, it won't design an amplifier. We look at stuff. And even if it does, it just does it for, there are some people who have worked on kind of synthesis for analog, and there are some limited implementations. But what happens is that you can't come up with new topologies with the simulator, even if you have synthesis tool, and they are not very good anyway. But so the problem, the main reason for trying to understand, do a lot of analysis that we do in this class, is to be able to design. Right? Yeah, you had a comment or question?
Yeah, I was just wondering if the simulator doesn't actually use these equations, do you just plug in the differential equations that we saw? Is that how the simulator does it?
No, well, it doesn't use these equations. Well, okay, let me put it this way. The simulators, for instance, for MOSFET has a large number of different models that you can choose from. So if you use level 1, you pretty much are using these equations. Just the kind of the most basic, hence the level 1, right? And there's a modified version of that which is level 3 and almost which captures some of the other effects that we'll talk about. But the equations they use, they're not differential equations. The expressions that we use for currents and all those things, they are not the original differential equations. They are more sophisticated models captured through the analysis physics, but most of the DC type of models are basically partially curve fitting models. So they are semi-empirical. In the the sense that they look at the device and say, well, what's the best fit for this kind of transistor? They make all sorts of transistors with different things at some point, and say, well, what is the physics? So it has to have this kind of behavior, but I can change this exponent and this coefficient to make it fit better. And nowadays, all of that is done through computers. So it's basically a semi-empirical curve fitting model. But it doesn't solve the differential equations by the time. If you want to do that, there are different kinds of simulators. So the simulator we're talking about here are circuit simulators like SPICE, which are implemented in cadence, ADS, different kinds of things. But there are device simulators that actually do what you just said. Right? Like Pisces and Medici and all those device simulators, they actually go and look at the carrier equations and the differential equations and they solve those. But all you can solve with those things is one transistor. So you can design a transistor, well, this is the dimension, this is the distribution here, this is the thickness of the gate, this is the material, blah, 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 and let it run for a couple of hours and it spits out what the IV characteristic looks like. Which is a lot more accurate than our first order model, obviously, because it solves the differential equation. So there are different levels of simulators. But that solves one transistor. But the point that I would like to emphasize, and I will get back to over and over in this course, is that the reason we do this analysis is, although it is fun, is not just for fun. It's for us to gain intuition toward design. So when it comes to design, we can think about it in a clear way, and we'll go through many examples of design through this class, right? See how we start from something simple that doesn't quite do what we wanted to do, and we modify it to understand what is the limiting factor. The key is to understand where the bottleneck is in the design. So start from the simplest design you can think of, and see if it does your job. If it does the job that you want it to do, fine, you're done. If not, you got to go and look at it and say what is the limiting factor, and then what you can change. Most of these changes are topological changes. It's not just parameter changes. So we threw in several additional transistors in a different way, or we reconnected, or we changed the way we are doing it completely. And that's the part that's important. That's the part that no computer can do. Okay? So that's the point. And we'll see many examples of this. And you will see that if you don't think about it this way, just kind of design-oriented analysis, you will be stuck in local minima of the design space. So what happens is that you will just start modifying and tweaking the circuit, and it will improve a little bit, but not a whole lot. We'll get to that. Okay, any questions? Alright, so that was a quick review of what we said last time, but I think it's important for us to capture this, because we will use some of these expressions in the material. Now, one of the interesting things that happens is that we saw, even if we can see from these expressions, one thing we can see is that the speed of the device really is controlled by the time it takes for the carriers to get from one side to the other, right? That's how fast it can react. You want this time to be as short as possible. And it does two things for you. If you do that, first of all, it gives you more current for a given charge, right? And second, it can happen on a faster scale. On a faster time frame. So we look at this and see what it depends on. Really, on the first order, what does it depend on? So let's say the charge distribution is kind of uniform. If the charge distribution was uniform, the time it takes for an average electron to get from here to there is what? It's the drift velocity, the distance L, channel length, divided by the drift velocity, right? So if you want to make this faster, what can you do? The drift velocity is kind of determined by the electric field and all those things, so you can apply a larger field but up to a certain point, right? But one of the easy things you could do, at least on the surface, is to make the channel length shorter and shorter. The shorter you make it, the faster it should get. Of course, it has to travel a smaller distance, shorter distance. So that's the basis for scaling of the MOSFET. MOSFETs. You want to make it as small as possible for it to be as fast as possible, and of course to fit as many of them as possible on the same chip. So when you start doing that, initially it worked out nicely. So initially, MOSFETs 30 years ago were something like 5 microns wide, or 10 microns wide. And they were fine, and then at some point they went from 10 microns, so well, let's make it 5 microns. And then it became faster, and they became smaller, and that was basically what gave rise to the Moore's law. Right? So the number of transistors went up, they became faster, they became more effective, and people said, well, this is great. Of course, there was a little more to it than that, just that, because you have, if you want to think about scaling in a proper fashion, you have to also scale all the other dimensions at the same time. If you want to do it properly, there's a whole theory of how you can scale a transistor. At least initially, the theory was you want to make all the depletion regions the same, scale them by the same factor, K. Right? So you want to scale it down, you want to scale the gate thickness, you want to scale the channel length, you want to scale the voltages so the electric fields remain constant. And everything scales down. And up to a certain point it worked nicely, but there was a problem. The problem is that, well, if you just want to scale down the electric field constantly, then the voltages became ridiculously small. So for any practical purposes, they were not useful transistors. If you wanted to scale it down, nowadays it would have been at 0.05 or 0.03 volts supply voltage. And it's not very useful because, first of all, the noise margin is very small for digital circuitry. And on top of that, also you can't design a whole lot of useful analog circuits with that kind of supply voltage. So they had to compromise on something. So they said, well, we can't really scale the voltage linearly, the supply voltage. So we are going to keep that and then kind of let it go down at a slower rate. As we make better and better, smaller and smaller transistors. And as a result of that, you ended up in a situation that you have a very large electric field across the transistor, across the channel. And therefore, if you remember, when we were talking about the drift velocity, so this is kind of, we're talking about velocity saturation. If you remember, we talked about the drift velocity versus the electric field. And we saw that initially it was kind of a linear dependence, right? Because of that overlay, large random thermal movement. But at some point, when the drift velocity started became comparable, or we can't get even close to the thermal velocity of the electrons, then it couldn't grow linearly anymore, right? So we had this velocity saturation phenomenon, VSAT. Okay, there was a maximum velocity at some point achieved for maximum electric field. Now, the problem is that nowadays the devices we make, and they have been for a while, actually for the last 10 years at least, or maybe even more, last 15 years, we are in a velocity saturation mode. So that basic assumption that V drift is simply mu n E does not hold anymore. Not in that form. So, well, of course, not for the shortest channel transistors, but you know that the channel length L is a design parameter, so you can actually play with that and make a larger transistor. That's fine, but that won't be the fastest transistor. So for the fastest transistors that you can make in a process, you have a problem with this. Now, actually you can model this drift velocity saturation with an expression similar to that. So if you mu naught is basically the slope at zero, low electric field. So this is mu naught. Then you can write the velocity as follows. You can capture this through a second correction term, like that. So you can see an ESAT is the electric field at which the velocity is half the saturation velocity. This is the saturation electric field. Okay? So if you define it this way, you will see that in low electric field, this term is small. So you basically reduce it to that original expression that you have. And as the electric field goes higher and higher, this becomes larger. So in the limit, basically, you have mu ESAT. And the way you define it, basically, what mu ESAT. So you can see that your drift velocity is not proportional. Or in other words, if you look at the mobility versus the electric field, it's initially constant but starts dropping off. So this is mu naught, the low field mobility. Because of this effect. Now, what is the impact of the transistor performance? What is the impact on the equations we wrote? Well, let's look at it. Let's look at a very simple expression, right? So let's first look at the first order model we had. We said, well, the channel charge. What was the channel charge? Ballpark. I mean, we don't even need to integrate it. Let's say it's almost constant across the channel. Just really simplistic. for the electric charge or an average electron to get from the left to from the source to the drain? L over V drift, right? But now the difference is that, let's say the channel length is very short and the voltage across that is large, so the electric field is high. In that case, in the limit, basically this is limited by V sat, right? In the limit, that's what it's going to be. It's going to be saturated. And basically you can rewrite it as L over mu E sat. Okay? Something like that. Now, what is the current? So the current, basically, again, these are approximate, is approximately Q over tau, which is going to be what? You can see you got Cox WL VGS minus PT divided by L mu n V sat. I'm sorry, V sat, L over V sat. Which you can write as, so you can see L's cancel. So you have Cox W VGS minus VT V sat, or you can write it as mu n Cox W E sat VGS minus VT. Actually, the way it's defined, E sat is defined as this from E sat over 2. Doesn't matter. So the point to take away from here is that now you can see the behavior is different. You can see that the behavior, instead of being square law, the dependence on the VGS, instead of being square law, it's linear. So we don't even have that square law strong dependence. It has become linear with VGS in the deeply saturated transistor. And the other interesting thing is that there's no dependence on L. So beyond this point, or close to this point and after, if I make my device smaller, the current will not increase. So it seems that I have reached the maximum, or the best I could achieve for this. Well, I still can help with something else. Of course, I can try to improve my Cox. How can I increase my Cox if I want to get higher current for a given change in VGS?
Make your gate offset
thinner, right? So if I make it thinner. Or somehow if I could improve my mobility, that's kind of harder to do, but if I could make it out of a different kind of material that has a higher mobility, maybe that helps. Or something that has a higher ESAT, that would help. Or simply apply larger VGS, still, I can get more current. But you can see that it's not as strong and I can't do much about it. Now, does that mean that we can't improve the speed of the transistor anymore? As we shrink it? Should we stop shrinking the transistor, scaling it down based on this expression? If I want to make it faster? Or does it still help? Well, we'll answer that quantitatively in a few minutes. But before we do that, I want you to think about it qualitatively, intuitively. Think about it. What are the two things that determine the speed? You're basically charging and discharging capacitors, right? So what is the primary capacitor here if you're charging? You can think about it as the gate oxide capacitance, right? You're charging and discharging this. What is that capacitance? That's Cox times W times L, right? The area times capacitance per unit area. So I'm charging and discharging that capacitance. So when I shrank my L, my transistor, the length of the channel, before I gained, because of two things. My speed went up because of two effects. One is that my capacitance became smaller, because L became smaller, right? The area of the gate became smaller. And the other one was that I got more current, which was more bang for my buck, for a given change in VGS. Because that depended on L too, right? ID had a W over L in its expression. But now I have lost the second effect. Basically, I can't get more current. But the speed by which I can charge and discharge a capacitor depends both on the current and the capacitor. I have reduced the size of my capacitor. And we'll see this quantitatively in a few minutes. So it does still help, it turns out. But not as much. So we'll see. Now, in addition to this velocity saturated current, there are also other changes that happen when you go to a small channel. So for instance, the threshold, the small dimension in general, the threshold voltage also changes. So let's see why that happens. Now, think about our discussion about the threshold voltage of the MOSFET and the MOS cap, right? There were several different terms in that expression for the threshold voltage. One of the, and they accounted for different things that the threshold, the voltage on the gate has to account for. One of the things was to compensate the voltage, the electric field generated by the depletion region, right? In other words, to create the depletion region, you need to have a certain amount of VGS first. You saw that, right? Because you have to apply a certain level of voltage to the gate to create first the depletion region, and then you could go to inversion. Now, what if my part of my depletion region is already there? Well, think about it. If I just take an N plus, this is the kind of simple NMOS, right? N plus, N plus. You already have, and this is the substrate. You already have two depletion regions here, right? Is that right? So, I have a little bit less depletion region to make when I apply my VGS. That effect always exists. But now, for a long channel transistor, this is a small fraction of the total depletion region that I have to generate. Right? I have to make this much depletion. But now, if I make it a short channel transistor, if these are very close to each other, a good chunk of my depletion region is already made. Right? So I have to only create a little bit more extra depletion region. And that tells you what? Would it lower your VT or higher your VT? In other words, do I need a higher voltage to turn this transistor on, or do I need a lower voltage? Lower voltage, right? Exactly. So this is a short channel effect. So what happens is that if you look at L and the VT, at low voltages, VT goes low channeling, VT drops. So how do you deal with that? Well, depends on what you want your VT to be, because we have this one parameter we control, right? QI, the implanted charge. We said at the end of the day, you could implant a certain amount of charge in there to make sure that you get the right VT. So if you want to keep the VT constant, it's not necessarily the case, but if you wanted to keep it constant, you had to implant more implant charge. If you didn't want to keep it constant, you were happy with it, you just lived with it. But it is an effect that happens. But in a given process technology, right, the implant charge is fixed. You can't change that once the chip is made. It's fixed for all transistors because it's not in the batch process. So now, the transistors that have shorter channel length are bound to have smaller VT. The VT is not even constant, and you go to short channels. So that's something to keep in mind. Now, there's another effect. How about the W, the width of the device? Do you think that would affect the VT? Well, why wouldn't it affect the VT right, initially? But let's think about this as a truly three-dimensional device. So, if this is your MOSFET, I'm not going to show all the details of it. So, this is the drain and source. Right? So, the electric field that you apply to the gate, right? This is like a capacitor, but like any other capacitor, there's fringe field. So if you look at it this way, from the side, this is the gate, this is the drain and source, there's a little bit of electric field here. Now, the depletion region is extended laterally in this direction too. So you have a little bit of depletion region outside the transistor. So if you look at the top-down view, this being the source, drain, gate, you're forming depletion region here and there because of this extra electric field. So that means that you have a little bit more depletion region to make than you thought because of this three-dimensional effect, right? Now, again, if the width of the transistor is large, that's not a big deal because it's a small fraction of the total depletion region that you have to make. But if the width of the transistor is very small, that becomes a reasonably large fraction of the total depletion region. So what does that mean in terms of VT, in terms of versus W? If I look at my VT versus W, what do I expect to happen when I go to really small W's? Do I need more voltage or less voltage? More voltage, right? Because this extra depletion region that I have to make becomes a larger fraction of the whole thing. So for small W's, really small widths, my threshold voltage goes up. so you may say, well, why does my transistor, this transistor have a slightly different threshold voltage than that transistor? Or, in reality, in the lab, you may see this. So that explains what happens there. Okay, any questions? Alright. Okay, so this is basically the kind of the level of details that we'll talk about in terms of the device physics. But let's go to the MOSFET models and try to see how we can come up with a small signal model, a linearized model, the same way that we did for the bipolar transistor, and derive a small signal model for the MOSFET. So whenever we wanted to look at it from a small signal perspective, we can start using that model from the beginning. Okay, now where is the transistor action? So let me just, I think probably the best thing I can do is to redraw my transistor quickly here. I don't want to back. And rewrite my expression. So let's talk about the pinch-off region, because that's the region we are most interested in. So primarily in the pinch-off region, the first order effect was that we had this square law for a long channel transistor. We had this square law dependence, okay, on the current. That was the first order. Got W over L. Mu n C ox over 2, W over L, VGS minus VT. Now, where's the transistor action is a change, you can see, it's a current, it's a voltage controlled current. Kind of in a similar way that the bipolar transistor was, right? There you had a VBE that controlled IC. Here you have a VGS that controlled ID. The dependence is different. It's not as strong as a bipolar transistor, as you can see. That's an exponential dependence. This is a quadratic dependence. But still, I can define a basic transistor action, GM, the transconductance. Which is by definition, DID dVGS. In a similar way that for bipolar transistor it was DIC dVBE. Now what is that? Well, you just have to differentiate that. It makes it simple. It's mu n C ox W over L VGS minus VT. So if you know your VGS, this is a large signal VGS, quietness at operation point, that tells you what your transconductance is. In other words, this is another way of saying the same thing. So if you look at ID versus VGS curves for a bipolar transistor, based on the simplified model, the transistor is off up to VT. We know there's some threshold current here, really. And then you go up quadratically. Now, what it is that at a given VGS, capital VGS, if I apply a small signal fluctuation, VGS, what kind of fluctuations I can expect around my quiescent capital ID. In other words, ID. Right? So this quantity is really nothing but the ratio of ID over VGS, which is the slope of this line. As is evident from the derivative. Now, that tells you it's determined by VGS on that device, which is fine, but sometimes you have the VGS, and sometimes you know the ID, sometimes you know the current. You have biased the transistor with the current source, for instance, and you know what your ID is. So it's useful to have this expression both in terms of VGS and ID. So let's try to write an expression in terms of ID. Now, to write it in terms of ID, I have to use this expression, this equation. So I want to turn this into something that I can relate to that. So I notice one thing. If I take that equation, multiply it by 2 to get rid of this 2, multiply it by mu n C ox to get mu n squared C ox squared, and multiply by W over L to get W squared L squared. So I'm multiplying all of that, so ID, by this, I get mu n squared, this whole thing is mu n squared, W squared, C ox squared, W squared, L squared, this whole thing squared. And if I take square root of that, it simply becomes that. I'm just solving it in terms of ID. I multiplied that by these terms to get this. That's squared and then squared. So if I want it in terms of ID, that's my expression. If I want it in terms of VGS, that's my expression. Now, do you remember the GM for the bipolar transistor? What was it, the expression? That was actually a simpler expression. That's one thing you should remember. Start simple thing, but what? It was IC over VT. Right? The collector current divided by the thermal voltage, 25.8 millivolts kT over T. Right? That VT had, by the way, that VT has nothing to do with this VT. Again, that's an unfortunate coincidence. So they have nothing to do. That's kT over T. So in the case of a bipolar transistor, the dependence was linear. So if you wanted to double your transconductance, you only needed to double your current. In a MOSFET, you need to quadruple your current to double your transconductance. So what does that mean? Which one is a better device inherently? Which one is a stronger device inherently? The BJT, right? Because of that strong linear dependence, BJT is a stronger device. It has more drive, well, more accurately, it has more drive capability. It can drive more current. Right? And that's why, still, I mean, in the silicon domain, the fastest transistors are BJTs. Although MOSFETs are catching up quite fast, but they are not still as fast as BJTs, and they don't have as much drive capability as BJTs. It doesn't necessarily mean that they don't have other advantages. They have a lot of other advantages, MOSFETs and performance. And that's why both of them are in use today, even today. And extensively, actually. Both of them are used. So, now, so that's the transconductance of the transistor, and we know what it is. So that's the base, the most essential part of the transistor. That's the good part of the transistor. Now, pretty much almost everything else that we will have from now on is bad things, parasitics. Like the bipolar transistor, there was one good thing about it, which was the transistor, the transisting part of the transistor. And everything else was kind of the things that impeded your operation. So let's start building up our small signal model. So again, this is a current which flows between the drain and source. So let's say this is the drain, this is the source, and it's controlled by the voltage across, so this is the gate, the VGS. The voltage across, the small signal voltage across the gate source, and that simply is GM-VGS, which is evident from that expression. That's another way of writing that red expression up there. So GM is I over VGS. Okay? Now, so that's the basic transistor point. Now, what else do we have? You remember in the case of a bipolar transistor, we had this R pi, a resistor between the gate and source, right? Which came from basically the way we defined it in that case was, it was R pi was DIB, DB, right? Inverse. Now, in this case, do I have to worry about that? Well, in this case, it would be DIG, DVGS, right? Base corresponds to the gate, source corresponds to the emitter, and the drain corresponds to the collector. So, do I have to worry about this? What is this? Well, at least based on the simplified, what is my drain current? What's my gate current in this model? Small signal gate current at low frequencies.
Zero.
Well, at least based on this model, it's zero, right? It's a capacitor, so there's no DC current flowing into it. So based on this model, my R pi, or equivalent to what it would have been, is infinite, because this is derivative of zero with respect to something which is zero, so it's 1 over 0 is infinity. So it's an open circuit from that perspective. Now, the truth is that this is not true anymore. And I'll tell you why. With very small transistors, what you have is a gate that's extremely thin, right? You can have basically a 2 nanometer gate, oxide. Now 2 nanometers is how many angstroms? 20 angstroms, right? Silicon dioxide lattice spacing is about 3 angstroms. But that's something like 6 atoms, 5 or 6 atoms. So the gate oxide today is about 5 or 6 atoms thick. Literally. And it's actually even becoming thinner and thinner. Now, if you have something that's that thin, we know from quantum mechanics something interesting can happen. If you have a barrier that's very thin, a potential barrier. Remember, this is a potential barrier, right? You remember the Venn diagram that we had when we were calculating the threshold voltage, right? So this is very thin. What can happen? Yeah, tunneling. The electrons literally tunnel through the gate. And it happens. and therefore you have the gate current. It's not, for a single transistor, it's not very large. It's in the range of hundreds of picoamps, and it depends, of course, on the gate offset and a lot of other parameters, so it can vary a great deal. It's picoamps, nanoamps kind of things. But think about it. Let's say it's 100 picoamps, right, gate current. And you say, well, it doesn't sound like a major problem, right? It's not a big problem, isn't it? Is it? It depends on what you're making. If you're making it some sort of a chip with 100 million transistors, then that can add up. Do we have chips with 100 million transistors? You bet. Microprocessors. Do we have chips with billions of transistors? Memory. Think about your flash memories, right? I mean, you can buy an 8 gigabyte, right? Even if there's one transistor per bit, that's the minimum, right? So 1 transistor per bit, 8 gigabytes, that's 64 gigabits, minimum. No parity, nothing, right? No sense amplifiers, no drive circuitry, no board line, bit line, nothing, right? Just the bits. That's 64 billion bits. Minimum 64 billion transistors. That's a lot. Nanoamps and picoamps can add up very quickly in that situation. And actually, this is a problem in today's microprocessor. Because microprocessors today are not limited by the number of transistors you can actually reliably make. Interesting enough, although you're making hundreds of millions of transistors. They are limited by how much power you can dissipate, how much heat you can dissipate, how you can get the heat out. So that's what limits their performance, primarily. First order, I mean, there are a lot of things, but that's the first order effect. Now, the heat, the temperature that is determined by how much current you draw from the supply. So if you have to draw this extra current through the gate, drive the gate, then you have a problem, right? So you can see these are real effects, and because of that, then nowadays, if you really want to model a really short channel device, like kind of a 45 nanometer or 65 nanometer channel like a transistor, you have to really put some resistor there to account for that. Then you can do that. But for most of the circuits we are designing, and most of the analog circuits, that's not a problem. That's not something that we care about too much, because of the fact that we have, first of all, we don't use 65, 45 nanometers often for a lot of analog circuits. And the other thing is that also the current flowing through one or two of them is not very significant. We're not using a whole lot of transistors. But you have to be aware of this, and this can become a limiting factor even in certain analog cases. I'll talk about one or two examples of where this can become significant, and you may have to take it into account. Now, this is why it's important to understand device physics when you design circuits. Because as the dimensions change, these equations change. So 20 years from now, the equations you apply may be slightly different, but if you understand the basic principles, you can always rederive them for the thing. Then you understand what will change if there's a quantitative or qualitative change in the transistor. Alright, so that's the GM. So that was the basic part of the transistor. Now what else? So I don't have to worry about an R pi, so I can leave that open for now. What else do I have? You remember I argued that there is a second transistor reading there, which is basically the VSB. The changes in the threshold can also modulate the current, right? So if I look at my changes in the current, if I keep everything constant and change the bulk potential with respect to source, that can result in a change in the current of the transistor, right? So in other words, I have to worry about another GM, or in other words, a GMB for the bulk, which by definition is DID dVt. I have to look at the variations of, I'm sorry, not dVt, VSB. This is, just want to make sure that, well, I define, actually, because of the way it's defined, we have to use dVs. Okay? DID dVs. Now, that's another effect, another change in the current due to a voltage. So that second voltage can modulate things. So let's calculate that. How do I calculate it? Well, again, I look at that expression, right? I differentiate that with respect to. So all of these terms are constant. So it's mu n, Cox over 2, W over L. Now, it's the derivative of this thing times the derivative of what is inside with respect to VBS. So it is the derivative of that thing that cancels this 2 and gives me a VGS minus V. right? And then I have a minus sign because of the VT, so I get a minus sign here. And it's going to be dVT, dVDS. Okay? Now what is dVT, dVDS? Well, I know what VT is. VT is VT naught plus gamma square root of 2 phi f plus VSV minus square root of 2 phi f. Okay? Right. What is that derivative? What is dVT, dVDS? These are constant terms. This is the only term that depends on that. So I get gamma, and this thing to the power of 1/2. So I get this to the power of minus 1/2. So I get 1 over square root of 2 phi f plus VSP times the derivative of the argument, which is dVSB to dVBS, which is minus 1. Okay? So that's the whole thing that I get. And basically, look at this. And this is what I have from the remaining term. And now I can actually define this as, I define this as chi. Okay, so I give it a name. Because it doesn't change. See, it's a weak function of source fault voltage. So the gamma was constant. So this thing I can rewrite as, well, I guess I call this minus chi, because I want to get rid of that minus sign, which cancels this minus sign. So I get this whole thing times chi. So this is chi, or more accurately, minus chi. Right? Now, what is this? What is this? That's simply Gm. So this is Gm times chi. In other words, I'm saying that chi is simply the ratio of GMB to Gm, which is given by this expression. But I remember what what gamma was, right? Do you remember what gamma was? Gamma was 1 over Cox and then it was times 2q n. In this case, it would be Na epsilon silicon divided by that square root. So I absorb that in 2 phi f plus VSP. Now, what is this quantity? What does it look like? We have a quantity that looks very much like that. Kind of a capacitance. It's not, is it? The depletion capacitance. You remember the expression we had for the capacitance of the depletion region? This is actually the capacitance of this depletion region. This depletion. Well, it's at one side of capacitance. That's why you don't have the ND. It was 1 over NA plus 1 over ND, but you don't have the other side of it. You just have only one side of the capacitance. So it's nothing but the CJC, or well, let's call it CJ, the CJD for the depletion capacitance, divided by Cox. So what it is, it basically tells you that the strength of this bulk transistor, the ratio of the strength of this bulk transistor to the main transistor, is the same as the ratio of the bulk capacitance, the depletion capacitance, to the oxide capacitance. In other words, the ratio of the JFET to the MOSFET, because you're forming a JFET on the backside, right, is the ratio of the depletion capacitance to the oxide capacitance, which is not that surprising either, because they are both field effect devices, right? They're controlled through the electric field. So the one that's more strongly coupled to the channel will control it more strongly. And in our model for the transistor, that corresponds to a change in the drain voltage, drain source voltage. So it's a GMB VDS. And VDS, this is the bulk. So this is the fourth terminal, whatever it is connected. So whatever that terminal is, it's called bulk. So VDS is this voltage. Now I showed it in a different color because in many cases, this is a parasitic effect. This harms your performance. There are some cases, limited though, where this can be actually helpful. So you can use both of these transistors in a kind of coherent way. We'll see those. But you have to be mindful of that transistor. Now, what else do we have? Well, the other thing that we have is the dependence. We saw that this expression was needed to be corrected. There needed to be a second correction term, 1 plus lambda VDS, because of the channel length modulation. So we have this effective resistance between the output, the drain and the source, right? Like RO, the output resistance, similar to the bipolar transistor. And by definition, the way that works is simply, so RO by definition is DID dVDS minus 1, which you can easily show is simply lambda ID. I'm sorry, 1 over lambda ID. It's identical to the bipolar transistor derivation. Basically, you can differentiate that with respect to VDS. Okay? So you have this other term, so this parasitic term, RO, here. Just give it a second. Okay. So let's take a quick break here. Let's stop here for a second. And then when we come back, we'll continue discussing what other parasitics are there. And you derive the capacitances and all those things.